Thank you for having me here. I'm going to talk about quantum complexity and black holes in two different guises. Before I do, I should explain something that you may all be wondering, which is why when the high-energy physicists are speaking at a conference called Quantum Information in Cosmology, we won't stop talking about black holes. In other words, you might wonder, what do black holes have to do with cosmology? There's a somewhat flippant answer to this question, which is that there are lots of black holes in the universe. We see them, we hear them, we even do cosmology with them. But that is not, in fact, the answer to the question, why do we keep talking about black holes rather than cosmology. The answer is that both black holes and cosmology have event horizons. And so in the case of a black hole, that's manifest by the fact that if you jump into a black hole, you can't get out. In the case of cosmology, expanding exponentially under the influence of dark energy, it's manifest by the fact that if you get far enough away from me, you could get dragged away by the expansion of space-time and can never return. So both black holes and the universe as we currently understand it have event horizons. And the same...
This is an inside-out black hole.
That is poetic, but not particularly accurate. But I don't know, it depends what you're going for in your descriptions. They both have event horizons. For that reason, the same kinds of paradoxes of quantum gravity that sort of surround event horizons emerge in both cases. In fact, pretty much every paradox of one can be reformulated as a paradox of the other. But it turns out that thinking about these paradoxes in the cases of black holes is always, in every example I know, cleaner and more simply stated and more pressingly formulated than in the case of cosmological event horizons. Why?
The universe evaporating?
There is radiation coming from the horizon, than the cosmic event horizon, as well as from black hole event horizons. Whether or not that leads to the evaporation is a difficult question.
But there's an infinite amount of stuff out there, so it'll take forever for it to evaporate, right?
I'm not going to get drawn on that question. Getting ahead of myself here. Okay, so
what about
great. So for that reason, we think about black holes. Why are they simpler in black holes than in the case of a cosmological event horizon? Roughly speaking, it's because in black holes you have an Archimedean point that you can stand a long way away from the black hole and be removed from it. With the cosmic event horizon, there's nowhere really to stand in which you are sort of a very, very long way away from it, and you decouple from it. That makes black holes simpler. It might also make you think that there are paradoxes specifically associated with the non-existence of an Archimedean point in cosmology that do not arise in black holes. That actually tends not to be true, though it may eventually be true, but most of the paradoxes can be reformulated in the context of black holes. Okay, so that's why I'm talking about black holes. And I'm going to give not one but two talks today entitled Quantum Complexity and Black Holes. I'm going to hijack the first 5 minutes of my talk time to give a description of one kind of way in which I think that quantum complexity and the paradoxes of quantum gravity that emerge in black holes can arise. Yeah, do you have a pressing question?
I don't know when you're going to be able to answer this question, but I was wondering, and now you're motivated why you talk about quantum complexity and black holes, and the title is cosmology. Could you explain this cosmological event horizon
I gather you're not going to do it now.
Yeah, I'm not planning to do it now. Maybe that's
I would
something.
be very interested in like learning more about it. Like,
Well, thankfully, you should come back on Thursday when Andy is going to tell you about inflation and cosmological event horizons.
okay.
So maybe that's the time to ask your question. Okay, so I'm going to give a quick talk. Both of the talks I'm going to give are going to be quite speculative. The second one is going to be somewhat speculative, and the first one is going to be extremely speculative. But I hope you will bear with me. I do not typically speak about this first one, but given the talks that happened yesterday, I feel it's now or never. So here is it sort of naturally fits into that framework and sort of answers the question, what are Boltzmann brains good for? Okay. So sometimes in physics we can't do things, and sometimes that's just annoying, but sometimes it's actually essential to maintaining the consistency of the theory. The classic example of this is quantum complementarity, formulated somewhere near where I'm standing right now, where the fact that you cannot measure both the position and the momentum of a particle at the same time is essential to undergirding the consistency of quantum mechanics. If you could, you'd be in deep trouble. And today I'm going to give a somewhat in other words, this inability is like essential. It's not just sort of accidentally annoying. It's like essential to the consistency of the theory. And it's a big hint if you notice that you couldn't do it, you couldn't both measure position and momentum, that you should take that seriously as something that's telling you something about physics and not just something that's telling you something about your own inability to measure something. Today I'm going to give in this brief first talk, I'm going to give a sort of souped up version of complementarity appropriate to quantum gravity. Again, relying on the fact that there is something that you cannot do. And I'm going to argue that the fact that you cannot do this is essential to maintaining the consistency of quantum gravity and to avoiding paradox. And the particular paradox that I'm going to be interested in avoiding is what's called the firewall paradox. For today's purposes, you do not need to know what the firewall paradox is, except that it is a quantum paradox of black holes. I think there's also going to be a talk about that by Jonathan on Thursday, which you're going to talk more about this topic. And so the only thing you need to know about this for the purpose of the next 5 minutes is that what the firewall paradox is that Alice, a observer, stands a long way away from a black hole, gathers the Hawking radiation that comes out of the black hole, performs some computation, quantum computation, on that radiation, and then carrying the result of that computation jumps in to the black hole. That is not a paradox, that's just a bad idea. The paradox arises when you ask the question, what does Alice see when she falls into the black hole? And this is a classic paradox of quantum gravity. Why is it classic? It's because quantum mechanics tells you one thing, gives you one answer to what Alice sees. Gravity gives you another answer to what Alice sees. These two answers appear to be incompatible with one another, hence the paradox. Now there is an attempt, there have been a number of attempts to resolve the firewall paradox, which has been a big motivating example over the last half decade in physics. But there is one attempt that I'm going to mention now to resolve the paradox, which says that the paradox can be avoided in the following manner. It can be shown that the computation that Alice must do before jumping into the black hole in order to manifest the paradox is exponentially complex. As in, it takes a number of steps that goes like e to the entropy of the black hole. A very large number indeed. And so in order to perform this exponentially complex operation, this exponentially complex computation, Alice is going to need an exponential length of time. By the time she's done it, the black hole will have long since evaporated, and along with it, the firewall paradox. So there is no paradox to be resolved. Now, this is a true mathematical statement that it's an exponentially complicated operation for Alice to do, but people, including Jonathan, have pointed out that there are some problems with this attempt to evade the firewall paradox. The first problem being that you could conceivably insulate the black hole and just leave it sort of in a sealed box, and so that it didn't evaporate during the time that you were doing the computation. Another problem thing being is that you could conceivably pre-compute, as in first of all you do the computation on some matter that you're later going to collapse to form a black hole, and then you collapse it to form a black hole, and now you've already done the computation before the black hole's made.
Doesn't saying it's exponentially hard also imply that you've already told me what the dynamics of collapsing black holes is in a quantum sense, which is the one thing we don't have?
Right, so there are two things that are required in order to do this computation. One is a knowledge garnered somehow, perhaps through study of string theory or perhaps through experiment, of the dynamics of black holes, the quantum dynamics of black holes. But even if you understood all of that, it would still be exponentially many gates required to build the quantum circuit that would do it.
What the dynamics is.
That's true. There could be some.
Output something completely random and no computation will do it, or they could always output zero states.
So we believe that black hole evaporation is unitary.
That's a huge assumption.
Well, that is a huge assumption that is common to almost all people who play this game. Certainly, if you thought that,
Part of the paradox.
yeah, certainly if you thought that black hole evaporation was not unitary, you would definitely have avoided the firewall paradox. You would have a huge number of other paradoxes on your hands that I will not describe.
I don't think even assuming it unitary makes it an exponential calculation.
It's true. For example, the one example of a unitary operator is the identity operator, in which case it would not be a exponential computation. Or indeed a black hole. What has been shown is that unless there is some special structure to the Hamiltonian, that there is absolutely no reason to believe there is, that the computation required is exponential.
You don't think there's a special structure to the black hole?
It is generically the case that it would be exponential. In order for it not to be exponential, you would require there to be some special structure. For example, that it was the identity operator. There is no reason whatsoever to believe that the unitary that the black hole.
It's random either. That's just a nice ansatz that a lot of people have jumped on for no very good reason.
So I think what you can say is this is part of the paradox.
Right. Yeah. Certainly, if you want to propose a solution to the firewall paradox in which the laws of quantum gravity and string theory are just set up just perfectly in order that this computation is easy, you're more than welcome to make that proposal. But I think that requires considerably more brave assumptions than go into almost anything that's been said about that, possibly including the thing I'm about to say. Okay. So my proposal is not that you cannot do the computation. My proposal is that you can do the computation, but that doing the computation renders the original question moot. It renders what does she see moot. And why is that? Well, the reason in an equation that I probably should have written on the slide but didn't. So I told you that the time required to do the computation is believed to scale like E to the entropy of the black hole. And essentially my point is that the entropy of the black hole is much, much bigger than the entropy of Alice. And so what does that mean? Well, there's sort of two versions of this argument, one just on counting grounds and another on more semantic grounds, that in doing this computation, and doing this many steps of the computation, you will necessarily make virtual Alices in the memory of your machine. I'm not going to take any questions until I've run through the argument. So in doing this computation, there will necessarily be virtual Alices in the memory of your machine. One way to say that is just a pure counting argument. Another way to say it is that you're doing a unstructured error correcting code, is sort of what your error correction procedure, and that involves simulating basically everything that Alice could see as she falls into the black hole. So what that means, in other words, is that by the time you're done with this computation, you have one flesh and blood Alice who's living a long way away from the black hole, ready to jump into the black hole, and you have an exponentially large number of virtual Alices living in the virtual memory of your machine. And so now it doesn't really make sense to ask the question, what does Alice see? Because Alice sees everything. Alice sees, in fact, sort of everything that it's consistent for Alice to see when she jumps into the black hole. And so I'm going to, now you might just say, well, that's kind of annoying, but not a essential problem. But I'm going to propose that just like complementarity for quantum mechanics, this is a strong version of complementarity that arises in quantum gravity, which is to say that your theory is required to give well-defined questions to answers to well-defined questions. It is not required to give a well-defined answer to computations so complicated that they summon so many virtual Alices as to render the question of which Alice is the real one and which is the virtual one's moot. Okay, yeah.
Well, isn't it different to just